Hi, my name is Jackie, and my partner is Shirley, and today we'll be presenting on energy-based models and the frame problem as it applies to our work in Philosophy 250.
So first, we'll introduce, or rather reintroduce, the frame problem. The frame problem exists in traditional Go-Fi systems in their attempts to model the mind. The formal systems existing in classical AI results in the inability for computers to identify when and which facts are relevant, especially in a changing environment. It introduces the possibility of an infinite regress of frames, even just to rule out irrelevant facts. The robot and wagon example that we've seen in class perfectly describes how Go-Fi and first-order logic systems do not have the common sense knowledge that humans do to constantly process and update in their changing environment and to pick out what is relevant. Hubert Dreyfus in Why Heideggerian AI Failed and How Fixing It Would Require Making It More Heideggerian also describes the neural version of the frame problem, which is the binding problem. How does our brain maintain and connect facts in its representation of its current experience of the world to other facts that it knows? What and how does it bind significance and relevance to meaningless external inputs? We'll look at possible solutions to these problems in modern models and AI systems, which quite possibly eliminate the frame and binding problems altogether. One model to examine in particular is Walter Freeman's neurodynamic model. Freeman's neurodynamic model explores the idea that a sensory and perception system is trained and strengthened by past experiences. In Freeman's studies with rabbits, a rabbit's olfactory senses may be strengthened while eating a carrot because it discovers the smell of a carrot in the process. He derived these observations from the Hebbian rule that neurologically, synapses between neurons that fire together become stronger as long as there is a reward. This reward of getting to eat the carrot increases the significance of relevant details, like the smell of the carrot, that are identified in the midst of lots of background noise. The issue of binding is not relevant here. Instead of trying to bind and process input into a representation, the animal is primed to process relevant input on the basis of their significance, which is gleaned from past experiences.
Freeman's neurodynamic model of the brain is itself an energy-based model. More generally, in these energy-based models, each possible state of the brain or model has an associated energy level. An attractor is a point of low energy, where all of its neighboring states have higher energy than it. These energy-based systems want to be in a state that decreases energy as much as possible, so when a network state has a high energy, it will want to descend into a lower energy state and towards one of these attractors. With each new group of inputs, i.e. a new experience or environment, there are new brain states created that tend towards some minimum state, and these states are called these attractors basins of attraction. These basins are any set of states such that when the model is in that state, it will eventually descend and settle into that low energy attractor. The attractor basins help the network to identify and select what is meaningful. Like Freeman's neurodynamic model, attractors are created and reinforced through the Hebbian theory. Neurons that wire together, fire together. Any network state that ends up in an attractor is strengthened by decreasing the energy of the initial state, thereby increasing the significance of the initial network state and deepening the basin of attraction around the attractor. These models help to provide an alternate approach to mind design, allowing us to potentially avoid problems that are detrimental to other models upon which Go-Fi and N-Fi are based upon.
So, how do these models go about solving the frame problem? Well, representations are at the core of the binding problem and the frame problem itself. The implications of Freeman's model is that the brain does not necessarily process inputs into representations of the world, and that there is no exact linear causal relation between the world and our brains. Significance is not stored representationally in memory, but derived from previous experiences and identified by attractors. Significance and change can be accounted for with basins of attraction, as each attractor is strengthened with different inputs. The binding problem can be resolved by the significance inherent in this model that is updated with each new experience. Furthermore, with Freeman's model, brain states are discrete and any given input reshapes the attractor basin landscape. These state transitions are themselves discrete. Freeman describes that since the states and the events that the brain experiences in time and space are discrete, they can be modeled in computers as numbers. These numbers in a computer, which are discrete state transitions in the brain, are not representations of the world itself, just models of transitions from basin to basin. With this, Freeman's model reflects a new paradigm in mind design that dissolves the frame problem. With its model of the brain, the frame problem does not exist. Ultimately, this new phenomena meaningfully dissolves the frame problem by showing that it is irrelevant in our brains and gives potential to new AI systems that use energy-based models to model human intelligence.
One such approach to replicating these energy-based models in computers to create artificially intelligent systems is through something called a Hopfield network. These networks are also energy-based models that seem to be based on the concept of associative memory. In humans, we are able to associate information with certain entities. Even when given partial information on a subject, we are able to recall our complete knowledge about that thing. For example, if I told you that I go to a top-ranked university in Vancouver, which has its main campus near Pacific Spirit Park, you would know that I'm talking about UBC even without me explicitly mentioning it by name. At its core, a Hopfield network is a model that, like associative memory, can reconstruct data after being fed with partial or corrupt versions of that same data. The architecture of these networks is also very similar to connections networks in the sense that it is a network of units that are also interconnected. However, that's where the similarity ends. There are no input or output layers at all. The input is just an initial state of the network, and the network state evolves over time until it settles into a fixed output state. Conceptually, this harkens back to when we first talked about energy models. We can define a function E, the energy function, that depends on the state of the graph and the strengths of the connections between the units. The energy is reduced when the current network state is similar to the network state of the attractor. The network, thus, over time, will change its state so as to achieve the lowest energy possible, settling into these attractor basins, and thus achieving a state that is close to that of the attractor. By doing so, we can recover inputs from high energy states by just descending into the nearest basin of attraction. Here, we see that even when the input is changed and the network state is changed, it will once again descend into the nearest basin of attraction, which may be a different attractor than the initial one. When the network state eventually does settle into a new basin, the network can then readjust its connections and deepen the current basin of attraction. This is the Hebbian rule in effect, where any intermediate states that are similar, read wire together, will be more likely to settle into the attractor state and fire together. Thus, over time, the energy landscape will reflect certain significant inputs and be able to reconstruct those inputs from incomplete data. The significance of past experience is preserved in the attractor landscape. However, it is also important to note that each new attractor does not represent any such thing. Rather, the brain's current state is the result of the sum of the thing's past experience. This attractor landscape is correlated with the agent's experience of the changing significance of things in that world, possibly founding the basis for a genuine intentional arc. There are no causal connections between the world and brain, nor fixed library representations. Instead, each time a new significant input is encountered, how the model perceives the world changes so that the significance of the input is continually enriched through deepening the attractors. In conclusion, Hopfield networks proved to be a promising implementation of energy-based models in the field of AI and machine learning. Even recently, a paper discovered that modern transformer models, the type of neural networks that are the backbone of recent breakthroughs in AI, like BERT and GPT-3, show that there are underlying Hopfield-like properties to these networks. Maybe the associative properties of the Hopfield networks can help to explain the seemingly uncanny ability for GPT-3 to remain topically consistent and recall relevant facts through their dissolution of the frame problem. Thank you for listening to our presentation on energy-based models and the frame problem, and we hope you learned something new.